So for this third problem, where we're trying to justify, we're really trying to justify that no matter how close we want to get to the number 1, we can find an element of this set which is that close or closer to the number 1. Right? So you might say that there exist elements of this set which are arbitrarily close to the number 1 on the number line. So that's thinking about this claim here using a distance function framing. Right? So however close that we want to get to the number 1, so 1 maybe is right here, however close I want to get, so how close we are here is what epsilon is kind of telling us. It's the radius of this interval right here. So that's that little distance. However close we want to get to 1, we know we can always find an element x of my set which is that close. Okay? So you might think that the elements of this set are clustered arbitrarily close. There's infinitely many of them, if you like, arbitrarily close to the number 1. And so the algebra that gets us there, this is the step I wanted to talk about. A few of you, I noticed, this is a common thing right now, a few of you are too quick to try and hit this inequality here with the triangle inequality argument, right? And try and smash this apart. Before you think about smashing this inequality apart, think first about simplifying the quantity inside the absolute value bars. Because if we simplify 1 minus 1 over n minus 1, just using algebra, we end up with just absolute value of minus 1 over n. And it's going to be a lot easier for us to make an argument about that quantity. So how are we going to know that that quantity is less than epsilon? Well, let's keep going with the simplification. How do I simplify the absolute value of minus 1 over n? Is there a way that I can get rid of those absolute value bars, which is what I would need to do if I'm trying to get n by itself? How do I get rid of those absolute value bars?
Just make it 1 over n.
Yeah. And the intermediate step there is that we can take that minus sign and turn it into multiplication by -1, and then using the multiplicative property of absolute value, we can pull that minus 1 absolute value out. But what is the absolute value of minus 1?
1.
It's 1. And so that factor can just disappear and leave me with just absolute value of 1 over n. But what's the absolute value of 1 over n? How do we know that? Well, yeah, it's a fact, but why is it a fact?
Because can't you go like, the absolute value of 1 over the absolute value of n?
Okay, we certainly could. So I could move this down there. All right, I will take one more step off to the right here. Slide this piece this way. Okay, oops. There we go, equals. All right, so we're still now trying to justify why is the absolute value of n equal to n? What do we know about n? N's a natural number. And what's important about natural numbers that tells us why this is true? Say again?
Unbounded above.
It's unbounded above, yes, but that's not the reason that the absolute value of n is equal to n.
The absolute value of a natural number is that number. So
But why? But what property of the natural numbers tells us that that is so?
The natural numbers are positive.
All the natural numbers are positive. That's right. There we go. Thus, n must be greater than 0. And being positive is a sufficient condition for a number to equal its own absolute value. Right? And so it's in this form that we end up being able to say something. And what's the last step there for solving for n? This is how we'll wrap things up. If I want to get the n by itself, what am I doing here? I'm taking a reciprocal on both sides. And that turns into 1 over epsilon on the right-hand side. What's going to happen to this less than symbol? It flips. We go to bizarro world because taking the reciprocal is a decreasing operation, right? The larger a number is, the smaller its reciprocal will be. And therefore, when we take the reciprocal on both sides of an inequality, the inequality flips. And so what you end up needing to justify here is how we know there's a natural number that's greater than 1 over epsilon. And there's where the fact that natural numbers are unbounded plugs in to your argument.